Hi class, we continue our study in section 12.2 by talking about components of vectors and eventually moving into some vector arithmetic. Okay, so for some purposes it's best to introduce a coordinate system and treat vectors algebraically. So if we place the initial point of a vector A at the origin, as you can see right here in two-dimensional space and here in three-dimensional space, of a rectangular coordinate system, then the terminal point of A is the coordinates A1, A2, or in three-dimensional space A1, A2, A3, depending on whether you're occupying the for 2D or three-dimensional space. You'll notice here, this is how we're going to denote a vector using coordinate systems. So the bolded vector A, and it's going to get this special type of notation for the points. So instead of like a parentheses to denote a point, we use these little guys, these little brackets here, and then the endpoints of the vector. Okay, these coordinates are called components of A, and we write them as I was saying. Vector A in the two-dimensional system is A1, A2, and vector A in the three-dimensional system is A1, A2, A3. So we use notation like this for the ordered pair that refers to a vector so as not to confuse with the ordered pair with regular parentheses that refers to a point in the plane. So for instance, vectors that you see in figure 12 here are the equivalent to the vector OP. So like this vector OP right here tells us it's starting at the origin and goes to point 32. So it's telling us starting at the origin, ending point 32, and its terminal point is 32. Okay, what all those vectors have in common is that the terminal point is reached from the initial point by a displacement of 3 units to the right and 2 units upward. So look at all these different vectors. So even though they all have different starting points, they all represent the same type of, or the same vector, because you're going over 3 units and up 2. Okay, we can think of all these geometric vectors as representations of the algebraic vector A, which is 3, 2. So the particular representation OP from the origin to the point 3, 2 is called the position vector of point P. So the position vector starts at the origin here. Okay, so in 3 dimensions, the vector A here, the OP vector, is a position vector from the point A1, A2, A3. So here, just remember, position vector starts from the origin, goes over here. So this is another representation of A. It's just shifted X units and then Y units and then Z units over. So let's consider any other representation of that vector A, all right, where the initial point is some X1, Y1, and Z1, and whose terminal point is X2, Y2, Z2. So here's my vector A. Okay, but now what we're saying is it has some initial point that's not the origin and some terminal point that's not this exact same one here. Then we must have, as you can see here, all the values, okay, x1 plus a1 is equal to x2 and so on. Thus we have the following results. All right, if you're given the points a and b as listed here, the vector A with representation AB is given as the following. Okay, so A, what you're going to do here is you're just going to subtract each value of the x, the y's, and the z. And this right here will be a position vector that is equivalent to this vector AB. All right, so let's do an example. So let's find the vector represented by the directed line segment with initial point 2, -3, 4, and terminal point -2, 1, 1. All right, so by this formula right here, okay, we see that the vector corresponding to AB, well, you're just going to take -2, -2, 1, -3, 1, -4, and this would be the resulting vector right here. Next, I want to talk about the magnitude or length of a vector V. Is the length of any of its representations and is denoted by the symbol magnitude V, or an equivalent statement would be the magnitude V. Okay, and this is by using the distance formula to compute the length of a segment OP. We obtain the following formulas. If you're in 2 dimensions, the magnitude of a vector A, you just take its components and square them. You sum those squares and you take the square root. Same thing in 3-dimensional space. Square each component of the vector, sum them, and then take the square root. And that'll give you the magnitude or length of that vector. Notice that this works for OP, okay, where the initial point is O. All right, it's a little bit different if you don't have the initial points. You can convert it this way, okay, to get it to the position vector, and then use this formula. All right, so next, how do we add vectors algebraically? Figure 14 shows that if vector A is A1, A2, and vector B is B1, B2, then the sum of those vectors, A plus B, all you do is you add their corresponding components. You take A1, add it to B1, you take A2, add it to B2, and that's simply how you do vector addition. So in other words, to add algebraic vectors, we add corresponding components. Similarly, to subtract vectors, we just subtract their corresponding components. There's nothing overly difficult about that. All right, from similar triangles that we see in the figure below, we see that the components of CA are just multiplying. If you multiply the vector A by some constant C, you just get CA1 and CA2. So to multiply a vector by a scalar, we multiply each component by that scalar. That's all you have to do. All right, so again, if vector A is equal to A1, A2, and vector B is equal to B1, B2, then again, just to add the two vectors, you add the corresponding components. To subtract the two vectors, you subtract the corresponding components. And similarly, a scalar, you just multiply through to each components. Same exact concept if you want to extend this into 3 dimensions as in 2 dimensions. There's nothing extra you need to do there besides having the z coordinate or the z component. All right, next we denote by V2 the set of all 2-dimensional vectors, and by V3 the set of all 3-dimensional vectors. More generally, we consider the set Vn of all n-dimensional vectors. So an n-dimensional vector is just an ordered n tuple like you see here. And this is just where each of the components are real numbers and are called components of vector A. So V2 is 2-dimensional vector, V3 is 3-dimensional vector. For this class, we're mostly going to focus in V2, V3. We won't go to any higher dimensional vectors. All right, just a quick summary here of the properties of vectors. I won't go through all these in this video here, as you can see it in the slides and follow along in the class. But basically, the properties of general arithmetic will hold here for vectors as well. All right. Next, I want to talk about 3 vectors in V3 that play a special role. Okay, they're the vectors I, J, and K. Okay, and these are what are called standard basis vectors. So these are vectors that have length 1 and point in the direction of the positive x, y, and z axis. So vector I points in the x-axis, vector J points in the y-axis, and vector K points in the z-axis. Similarly, in 2 dimensions, we can just define it as I and J. You don't need Z, but you can see what I mean by these vectors here. Here's vector I. It has a magnitude of 1 and points along the x-axis. Vector J has a magnitude of 1 and points along the y-axis. And similarly, the only difference here is that you now have vector K, which points magnitude 1 along the z-axis. So if you have vector A, which can be written as components A1, A2, A3, then you can actually just write it as vector A is equal to the x component times I, plus the y component times J, plus the z component times K, always. So if you have a vector in V3, you can express it in terms of I, J, and K like this for following. If you have the vector 1, negative 2, 6, this would be equal to 1i minus 2j plus 6k. Okay, you can do the same thing in 2 dimensions, just without the k variable. This is just another common way to represent vectors. Okay, so what you can see here in figure 18 for the geometric interpretation of equations 3 and 2, and compare them with figure 17. So just all you're doing here to get vector A is you're adding the components of I and J here, and similarly in 3 dimensions, it's the same deal with the I, J, and K. Finally, I want to just talk about a unit vector. So a unit vector is a vector whose length is 1. Okay, so for instance, I, J, and K are all unit vectors. So in general, if the vector A is not equal to 0, then the unit vector is a vector that has the same direction, but whose magnitude is 1. So we'll always have vector u is going to be equal to the unit vector, okay, is going to be equal to 1 divided by the magnitude of a times the vector a. So which is just a divided by its magnitude. Okay, so in order to verify this, just let c equal 1 over the magnitude of a. Then u is equal to ca, and c is a positive scalar, and u is in the same direction. And you can see how it will all work out and just be equal to 1. All right, so basically this unit vector we'll talk about in the coming lectures. It's just a vector that points in the same direction as a but has length or magnitude 1.